This is Dean Schauer with HM Cragg. We are a Saft representative that can help anyone with their Saft needs. This webinar is in regards to the Saft Flexion product at 125 volts to work with switchgear and control gear in your substations. On the line with me is Dan Youngs with Saft. He has been in the industry for over 25 years and working in the energy and power industry, has experience with utility power plants, electric vehicles, and energy storage. He's been with Saft for 6 years, 4 years working on the energy and power industry and working with the lithium-ion product. He has a degree in electrical engineering from the Watson School of Engineering at Brigham University in New York State. And he is currently on the IEEE committee that is working on the lithium-ion guidance, I should say, that will come out from the IEEE here in a bit, whenever they have those finalized. So with that, I'm going to hand it over to Dan. Dan, the floor is yours.
All right, thank you, Dean. Yeah, as Dean said, I'm Dan Youngs. I'm a senior application engineer with Saft Batteries. I've been with Saft for 6 years. For the last 4 years, I've been working on industrial standby applications. And before that, I have about 20 years of experience with lithium-ion batteries in mobility, heavy-duty trucking and busing systems for automotive. And today we're going to talk about the Flexion product, which is our answer for lithium-ion industrial standby batteries. And so here's the agenda that we're going to go through. We're going to talk a little bit about who is Saft. I'm going to talk a little bit about lithium-ion battery technology, just to kind of set the stage. We're going to talk about some of the concerns that people have with lithium batteries. We're going to do a comparison to NiCad and lead acid. We'll look at some typical systems. We'll also look at the architecture of the Flexion battery. And then section 5 is some building codes. There's a lot of things changing in the building code area for lithium-ion batteries, so I have a summary of building codes. So anytime during the presentation that you have questions, Dean, I don't know what the mechanism is, if they raise their hand or just speak up, doesn't matter to me, but if you have a question along the way, feel free to interrupt and let's do it right then. If I know that the answer is coming up later, I might tell you just hang on, but let's try to deal with the questions as we go. I've got about an hour planned. I don't have a hard stop at an hour, but that's the target to try to get it done. So
yeah, if anyone wants to have a question, they can type their question in the chat box and I will mediate that, or they can raise their hand and then I will unmute you so that you can ask a question.
All right, thank you. So a little bit about Saft. Saft is an advanced battery company. We specialize in NiCad batteries and lithium-ion batteries. And these are some of the markets that we are very successful in. We're going to talk about industrial standby today. A little bit about Saft. We're owned by Total Energy. We're part of their gas and renewables division. They bought us about 4 years ago to enhance their renewables, and they also bought a solar company. They're very focused on moving forward in the next years with more and more green energy. Saft is about a 100-year-old company. We invest a lot of our money back into R&D to keep our batteries on a cutting edge. We're about 4,000 people. That's just Saft. Of course, Total is many, many more. and we're supported about 3,000 plus customers. This is kind of a global footprint of where we have plants and offices. You can see we have 4 plants in the US. 2 of them are lithium-ion, 1 of them is NiCad, and 1 of them is primary lithium. We also have plants in Europe, of course. We're a French-based company. And the product that we're going to talk about today is Flexion. The cells are manufactured in France, and the cabinets are put together in the Czech Republic. So here's a little intro to lithium-ion batteries. I like to recommend for anybody who is new to lithium-ion, get a hold of this IEEE guide for lithium-ion 1679.1. It's a really good primer on lithium-ion batteries, and it'll teach you an awful lot about lithium. It's a great resource. Saft was involved with writing it to a great extent. So I like to give you some resources and assign some homework. This is a really good piece for you to look into. I'd like to start out with why do we consider lithium-ion batteries in industrial markets? These are the main drivers, and the first 2 are the biggest drivers. The batteries are lighter and they have a smaller footprint. That's usually the problem we're trying to solve with lithium. The rest of the things, higher efficiency, the batteries don't take hardly any current on float charge, so you aren't always having a float charge current. They don't have to be equalized, so you don't have to put extra energy in to try to equalize the cells. They can be recharged faster, a lot more cycles than lead acid battery. Longer life than lead acid, and that brings you a lower total cost of ownership because you're not changing the batteries. Typically, we can put in a system to meet your design goals up to about 20 years. And we expect the battery to work for 20 years. It's not just a warranty for 20 years and we still expect to change it in 10. We expect the battery will still be functioning 20 years from now. Lithium-ion batteries come with an integrated supervision. So all the cells are monitored, the temperatures are monitored. You don't have to add on a battery monitor system because there's already included in the electronics. And there's less maintenance. There's no fluids to top off, there's no vents to check, there's no chemistry to check. The batteries are completely sealed, so your maintenance is really maybe visual inspection and possibly a load test if you want to do it. So we can talk some more about those things. If you don't need lighter and smaller, we can meet most of these other goals with NiCad also. So, we have 100 years history with NiCad, and it's a simpler battery. There's no electronics involved. So we don't push lithium as the only solution. We also offer very high quality NiCad batteries, which can give you longer life and lower cost of ownership. Of course, they would not have the integrated supervision. You really have to do a life cycle cost analysis per project, but this is just an example that I put in here. Typically, the lithium-ion battery becomes cheaper once you replace the first set of lead acid batteries. So you can see here that they do cost more to be put in, but over the life cycle, they can save you money. This graph was done in 2009. I should look for an update, but it was done by Frost and Sullivan. And this is all the batteries that we use. This is cell phones, consumer electronics, cars, all the batteries that were sold in 2009, 37% of them were lithium-ion. And we're starting to see much more lithium-ion going into industrial applications. Data centers are almost exclusively, new data centers are almost exclusively going with lithium, and industrial markets are becoming very interested for utilities also. A little bit of history, lithium-ion batteries were created or figured out in 1976, and Sony started building production cells in 1991. It takes a long time to go from the concept to a production cell. And in 1992, Saft entered the market with lithium-ion batteries. So we've been in the market for about 30 years. A little bit about how a lithium-ion cell is constructed. They're made of a positive and a negative electrode. Those are foils. Typically, the copper foil is used on the anode, and aluminum foil is used on the cathode. And then on those foils, we coat or paint the active materials onto the foils, and then they're constructed into a cell. This picture shows a cylindrical cell, which is sometimes we call it a jelly roll because it's rolled up and then put into an aluminum can. There's other types of cans. You can have square ones we call prismatic, or we can have pouch cells, which they remind me of a Pop-Tart. It's a foil enclosure that goes over the electrodes. The electrolyte is an organic salt, and typically the negative side has a graphite material on it, and the positive side has what we call the active materials, or in some cases metal oxides, and in other cases phosphate material. When you talk about lithium, there's a lot of different recipes to make lithium-ion batteries. You can use metal oxides, which are cobalt based. You can use nickel, cobalt, and aluminum mixed together, nickel, manganese, and cobalt, manganese oxides, iron phosphates. These are all cathode materials that we talk about. So typically, if you see these letters after your battery, NMC, NCA, LFP, that's telling you what's on the cathode, and they have different characteristics we're going to take a look at. With all of those, typically the anode is graphite, and there are some other anode materials. One that is in production and popular is the lithium titanate. So when you hear LTO, you're really talking about the anode. So those three letters are different than the three letters up above, which are cathode materials. When you're LTO, they're replacing the carbon with lithium titanate oxide. Each of those chemistries have different voltage curves, different voltage characteristics from full state of charge to empty. So the light blue one, the very flat one at the bottom, is the iron phosphate battery. And I'm going to focus on iron phosphate because that's what we use for lithium or for Flexion. You can see it has a lower voltage per cell, so around 3.3 volts nominal, where the other ones we consider 3.8 volt nominal. So with lithium iron phosphate, you get a lower energy density, but it has some benefits, mostly in safety that we're going to talk about, compared to the metal oxides. This does make the BMS, the battery management system, more complex for iron phosphate because we can't measure the voltage and tell you what the state of charge is. We can, when it's very close to empty and it starts down the steep curve, or when it's very close to full, we can tell what the state of charge is. But in the middle, it's very flat. And so what we do is we measure the current with a current sensor, and we count the amp hours during a discharge or during a charge to tell you the state of charge. With metal oxides, it's easier because you can just measure the voltage and you can tell where you are on the curve. Some of the differences between all the different chemistries that are out there, some, there's always trade-offs. Why do they make all those different chemistries? Well, if you're trying to maximize energy density and power density, you're going to go with metal oxides. If you're trying to maximize safety, you're going to go with either iron phosphate or lithium titanate. I don't have titanate on this graph, but you can see here that the safety rating of iron phosphate is higher than the others. And we're going to mostly consider here what happens during thermal runaway. We all hear the stories about the Boeing airplane and Tesla cars catching on fire and lithium-ion batteries catching on fire in utility applications for energy storage. So everybody's main concern is, hey, aren't these batteries flammable? And the answer is yes, they are, but there's a big difference between chemistries. And I'll show you the next slide. What is thermal runaway? So first we'll talk about metal oxides. So if we look at a temperature versus time graph, thermal runaway starts with some heat source. This could be generated from a short circuit or an internal defect or overcharging or over temperature, but some heat source gets started. That starts a reaction between the anode and the electrolyte, and that generates what we call low temperature reactions. So these temperatures are up to about maybe 300 degrees C. With metal oxides, these temperatures on these low temperature reactions trigger an oxygen release on the cathode of the battery, and that oxygen kind of adds oxygen to the fire, and it gets much higher, just like when you fan the flame of your campfire, you're adding oxygen to try to increase the fires. And that can lead to the metals decomposing and what we call thermite reactions. And now you're talking of temperatures approaching 1,000 degrees C. These are very high temperature reactions. And that often can lead to propagation within a module or within a cabinet, where one cell goes into thermal runaway. It gets so hot that it starts the one next to it, and then it becomes a domino effect through the battery. But with iron phosphate, the oxygen is bonded chemically much stronger on the cathode, so that oxygen is not released into the thermal runaway condition. So iron phosphate cuts the high temperature reactions from happening, and we don't get the oxygen release in the thermal runaway at the very high temperature. So this is a big difference between iron phosphate and the metal oxide versions. This is just a little, chemistry picture. It shows the positive materials, the separator, and the negative materials. And during charge, the ions migrate to the anode, and during discharge, they migrate back to the cathode. It's just everybody has to have this picture in their presentation. So that's what's going on. This is a look at how you build the cell for either power or for energy. So we can take the same size cell, the same container or case or jar, whatever word you want to use, and you can make a power cell or you can make an energy cell. A power cell will have, in our case, our power cell has 28 amp hours, and our energy cell has 43 amp hours. I'm sorry, 39 amp hours. So it's the same size cell. How do you change it? What you do on the power cell is you actually coat the separators much thinner with active materials, and this allows you to put more current carrying, more foils wrapped inside the same can. So you have more current carrying capacity, and you also have a faster access to the ions coming out of the thin coating. This gives you much higher power, but because the coatings are thin, they don't hold as many ions, so you get less energy. Conversely, for the energy cell, we coat the conductors thicker. We put more active materials so we can hold more ions, but that means we can't fit as much current carrying conductors inside, so we can't pull the same power out of that cell. So for instance, a power cell might be rated for 400 amps, and our energy cell might be rated for 200 amps. Don't quote me on those, but I have to look at the data sheet to tell you the exact number, but that's the idea. So we talked a little bit about cylindrical, prismatic, and pouch. This is just some pictures of what the pouch is on the bottom, prismatic in the middle, and the cylindrical on top. It's just a different way of tooling your battery line to build a different battery. And there's pros and cons. With the prismatic cells, you can pack them closer together and you can get more energy density inside the module. But because they're packed so closely together, it's more difficult to prevent the propagation or the domino effect. For Flexion, we use a cylindrical cell. These are easier to manufacture. And they also have, just because of their inherent shape, space between the cells in the module, which if one cell does go into thermal runaway, there's separation between that one and the next one, so there's less. This also helps with propagation of both the chemistry and the cell design and the module design. So we've talked about safety, we've talked about chemistry changes, we've talked about the cell and the module design a little bit, but here we put them all four what we call pillars of safety together to talk about how do you make a safe lithium-ion battery. And the first pillar is the materials and the process control. It's very important that you don't get any foreign materials wound up in the cell that could cause a short circuit. All of our batteries are built inside a clean room. I think it's Class A clean room. So, you know, when you walk inside there, you have to put on the whole bunny suit and a head nest and a face mask, and it's a very clean environment. We've talked about the choice of chemistries and how that can affect safety. For Flexion, we choose iron phosphate. We talked about cell design. It's not just cylindrical and module design, but it also is how do you handle venting. And in our cells, we provide a current interruption device, which if the cell vents, the pressure in the cell opens the circuit so that it takes that cell out of the current path, and that stops any more current from flowing in that cabinet. And then, excuse me, the last piece is system design. So with lithium-ion batteries, you have to measure every cell voltage, measure the current, measure the temperature. You have to have software monitoring all of that, and you have some controls to take the battery offline if it's going to go into thermal runaway, or if it gets, we stop way before then. If it gets too hot, we can disconnect the battery. If there's, well, actually, I can go to my next slide. these are the main functions of the battery management system. You have to protect against short circuits and overcurrents, overheating. So if we get to 70 degrees C, we're going to disconnect that battery so that it doesn't go hot enough to go into thermal runaway. So you have to design the battery room so that you are it's best to have the battery room be temperature controlled space for lithium-ion batteries. Overcharge is the easiest way to push a cell into thermal runaway. So the BMS has to stop a cell from being overcharged. So our system takes control of that with the BMS. If the charger goes out of line and starts to try to charge the battery too high, we will stop the charge. And I can show you a circuit diagram of how we do that coming up. We still connect to the load for discharges if we do that. And another one that's interesting with lithium-ion is if the battery is over discharged. And when I say over discharged, I'm talking about less than 2 volts per cell for most of the batteries. LTO, you can go a little bit lower than 2 volts per cell, but below 1 volt per cell for sure, the battery starts to dissolve the copper that's on the anode, and the copper can become a short circuit. So if it's been at a low voltage for an extended amount of time, you have to prevent the discharge or prevent recharging. All right, that's kind of the lithium-ion chemistry discussion. Here's a look at some of the stationary applications that we are pursuing to put Flexion batteries in. We've been successful in oil and gas. We've done a number of switchgear projects in substations. We've backed up process controls for like a water treatment plant. We also can go to 600 volts and do bigger things like data centers and other high voltage applications. I know we're focusing on 120 volts today, but we can go up to 600 volts. Maybe even we're actually coming out with a project supposed to be installed next year. We're just quoting it right now. That one's going to push us up into 690 volts, I think. But we have to recertify with UL for that. We've been successful in getting some jobs with backing up switchgear, mostly with privately owned switch yards like hospitals and that type of thing. We have one system in a utility substation so far. The utility market seems to be waiting for this IEEE lithium-ion guidance document that we're working on. They really want to be able to say the batteries are tested to this IEEE standard or they're sized to this IEEE standards, and that is being worked on by IEEE right now, and I think that's going to open up more utility-based, like NERC and FERC controlled substations. Of course, with switchgear applications, you have to have a very high reliability. The batteries protect very expensive equipment, so it's not so much about the price of the battery, it's more important what's the price of the equipment that you're backing up. And very long lives for substations, so we can get the battery designed up to 20 years. We can probably go to 25 if somebody really wants it. And I can discuss how we change the life of the battery by the sizing. All batteries fade capacity over time with calendar life. So, you know, we have a known rate of capacity loss. So we can design for 20 years, 15 years, 10 years, and tell you that the battery will still perform the duty cycle at the end of life. And we've talked about the low maintenance. There's very little maintenance with a lithium-ion battery. This is just a typical duty cycle for a switchgear. Typically, you have the trips and closes and then the continuous loads. And depending on your application, you tell us this profile, and then we can optimize the battery for that particular load and size the battery to your profile. It's kind of there's one mistake that often gets made is somebody says, hey, I have a 300 amp hour lead acid battery in my switch yard. I need a 300 amp hour lithium ion battery. But that's not a good way to size lithium, because typically the lead acid has to be oversized to handle the trip loads and the peak currents, where lithium can handle those loads very well. It's very good at power. Even our energy cell is much better than a lead acid cell at peak loads. So we often can have a smaller amp hour battery do the same job that a lead acid battery would be bigger. So when I size a battery, I really like to get this type of information from the customer. Here are some installation photos of jobs that we've done. And some of these are these ones over here. The taller cabinets are our 600 volt cabinets. The shorter cabinets on the right-hand side are our 120 volt systems. And in this, the one that's all the way to the left is a 120 volt system that's built into a cabinet. The customer bought the batteries from us and built them into his cabinet, and it has the rectifier and all built into the same enclosure. And that one's with a utility in the southeast. This is a switchgear comparison I put together. We're going to look at the footprint, the volume, total weight, and the price. This is a simple profile, 5 minutes continuous for 8 hours and 300 amps for 1 minute at the end. 120 volt system. These are some other parameters that we need to know the maximum temperature and the minimum temperature that the battery would need to run at. Like I said, I prefer to put lithium-ion batteries in a temperature controlled space so that I know they're always going to be at a particular temperature. Usually we shoot for 25 degrees C. But if it's going to be uncontrolled, I need to know the min and the max because that affects the discharge of the battery. This is a comparison chart. Here you can see what I was talking about with the lithium ion versus the lead acid. The lead acid needed 350 amp hours. The lithium ion actually needed about 100 amp hours to do this job, but I have 78 amp hour strings, so I needed 2 of them. So I actually have a 45% reserve capacity with 156 amp hours. If I could choose a smaller increment, I could have met this with a smaller battery, but 156 amp hours, 2 cabinets or 2 strings. And we'll look at each one of those individually with some graphics. So for the footprint, these 2 strings, we have a cabinet that is 24 inches by 20 inches. It doesn't have the height here, but it's a 93-inch tall cabinet. So we put 2 strings in one cabinet, kind of like that picture I showed you of the utility project in the southeast where it had 2 strings in one cabinet. So we have a very small footprint, 24 inches by 20 inches. And then you can see the comparison. So versus lead acid, we were, that's even smaller than 25% of the footprint. Of course, that's because we stacked it double high. If I don't have the room for that, I have a smaller cabinet, and that would take 2 of those, so it would be 48 inches by 20 inches. So on the volume comparison, again, you can see the lithium is much smaller in the volume. The weight is significant. We're about 25% of the weight of lead acid. We recently, we're working right now on production of some batteries for an offshore oil rig in the Gulf of Mexico. And this was their biggest consideration for that job, because weight is extremely expensive for them to build the structure of the offshore oil rig. And something like $12,000 per ton. It costs them in the structure. For every ton they add, they have to add about $12,000 to their structure. So this saved them a lot of money. Actually, it saved them more than the price of the battery. And then the initial price, this changes a lot with the project, but on this specific project, remember I had to oversize a 45%. So if I'm closer, typically I'm about the same price as a NiCad, but on smaller systems, depending on the increments, this is how it came out on that job for this comparison. So sometimes I'm closer to the NiCad number if the number of amp hours are closer. I have a couple pictures of grid systems because I know I'm talking to utilities. Saft is a leader in the big energy storage. I know this is not switchgear, but I just wanted to throw a couple pictures of containerized systems for wind, solar, grid. This is a different division, so if you ask me for information on these, I'll refer you to our energy storage group. And we have a couple of different containers. This one is more designed for power. You can see inside the cabinet, inside the container, there's a hallway to get in and service the batteries. But that really reduces the energy density because you have so much empty space in the hallway. So our new design, you access the modules from the outside by doors on the side of the container, and we put much bigger modules in to fill the whole container, so we get a lot more energy in that container. We call it the high energy container. But let's look at typical. This now is Flexion. This is our system for what we would use on industrial standby jobs. And we have different height cabinets, as I talked about a little bit. We can vary the number of modules to go from 120 volts up to 600. For 120 volt systems, we need 5 of those modules, the blue modules. In production, they're actually black, but on this picture, they're blue. We need 5 modules, plus the BMM and the protection unit, as those are parts of our battery management system. And then on the first cabinet, we call it the master cabinet, we have a LCD display so that you can get all the battery information displayed and you can know what's going on with the battery. Of course, we have an emergency stop button. If you hit that, it'll trip all the breakers. Every cabinet has a breaker for every string. So we'll talk more about that, but if you push the emergency button, of course, all of the breakers will trip, and you can hook to that remotely and put other buttons around the battery room if necessary. This is a look at how the battery module looks inside. Each module has 14 cells. For the 120 volt market, we use what we call a 23 volt module, and there's 7 cells in series and 2 cells in parallel inside that module. So we can change that circuit board at the top, that is the bus bar. And for our 46 volt modules, all 14 cells are in series. There's another circuit board that goes on top of this bus bar that measures all the voltages of every cell. It measures 3 temperatures inside the module, and it also performs what we call balancing. So the cells are all balanced to the same voltage when they're on float charge, so that all the cells are uniform, and we control them to all be the same voltage. And this means if there's a little bit of difference in capacities or self-discharge, all the cells are at the same voltage ready for a discharge. This is a picture of the module with the plastics all on. There is a communication from this module to the battery management module so that we can read all of the voltages and temperatures. And this also has the limits in it, safety circuits that are not software dependent. We have hardware comparators that if a cell goes out of range, even if our software is out to lunch, we have hardware protections for over temperature, over voltage, and under voltage built into this circuit board. So it's a level of redundancy for safety. The next module, the one with the breaker in it, is called the battery management module, or BMM. This has the breaker. It talks to all the modules with one communication channel, and then it talks to the master cabinet with another communication channel. This is where all the safety functions are contained. High temperature, low temperature, overcurrent, all of those that we mentioned earlier. The other interesting thing about this module is that inside it we have a DC to DC converter that goes from the battery voltage to the control voltage. So we generate our own 24 volts to run all of our battery management system inside this unit. This is different than our competitors where you have to run control power also to the battery. So that makes the battery installation much simpler, especially if you're replacing a lead acid battery where you don't need any control power and you don't have it available in your battery room. Flexion doesn't need it. It makes its own. The next unit we talk about is this protection module. We call it the IntelliConnect. And you can see here 2 diodes and 2 contactors in the blue circle. And I'll have a schematic about how this works, but this is how we protect from overcharge and over discharge. In some cases, we use both contactors, and in other cases, we only use one, and I can describe that. So this is a schematic of how the battery system works with the BMM, the modules, and the IntelliConnect unit, or the protection device. And you can see on the right-hand side, the battery, it goes first through the BMM, and that's where the circuit breaker is. In there, there's also a contactor. This is how we turn the battery on and off. We have a pre-charge circuit if necessary to charge any external capacitors before we close our contactors. And then in the IntelliConnect unit, we have these 2 contactors, K1 and K2. In some cases, we do not use K2, but let's talk about K1. You can see that the battery is discharging, the red arrow is discharging into the load, and I wish the arrow went up through the diode, but you can see the contactor is open. So even though the contactor is open, we still can discharge to the load. So we open K1 to prevent from overcharge. So in this picture, imagine that one of the cells is at its maximum voltage and we don't want any more. We don't want to be overcharged. We open K1 so that no more charge current can get into the battery, and then of course it's blocked by the diode D1. Similarly, on smaller systems, we can use K2 to interrupt over discharge. But on larger systems, we can't interrupt the peak load currents with K2. So on larger systems, we don't put K2 in. And for over discharge, we trip the circuit breaker in the BMM. Of course, that means someone on a large system, someone has to come out when the battery's completely discharged, it gets down to its lowest voltage, has no more energy, we go ahead and trip the circuit breaker. That means to bring it back on, somebody has to go and physically reset the breaker back on. If a smaller system, we can handle the current, we can do it with K2, and then the battery can automatically charge back up through the diode D2, and nobody would have to go there to reset any breakers. So on smaller systems, we can add the extra feature to make it more autonomous, less interaction with a human. The next piece of our battery management system is called the master battery monitor module, MBMM. This is an industrial PLC that talks to all the battery's strings to the BMM. So it monitors all of the strings and displays the information on the screen as if that's all one big battery. So you can look at the highest temperature in the whole set. You can look at the lowest and highest voltage in the whole set, currents for the whole battery group. And then you can also, with menus, drive down into information about each string, and then even you can display individual cell voltages in the whole battery on the display. This also provides communication out to the customer. So if a customer wants to monitor the battery externally, in a control room or remotely, you can connect to it with a number of different protocols. This is some of the information that's displayed on the screen. A lot of these are acronyms that don't make a lot of sense, but you can kind of get the sense for maximum cell voltages, maximum temperatures, states of charge, battery current, battery voltages, warnings and faults. If one of the strings is disconnected, you can tell, if you have a system with 4 strings, it'll tell you if one is disconnected, and then you can get this information. So these are the types of things that you can read both on the screen and remotely by the communication protocols. This is a look at charging versus temperature. When we're at room temperature, we can take full current, full charge current. This is for our power cell. PFE stands for the power iron phosphate cell. So one string of batteries you could charge at about 140 amps at room temperature. But as the temperature goes down, you have to charge slower. So this is where we start a discussion about smart chargers versus conventional chargers. We can use both, but a smart charger follows a message sent out by the battery communication. If we send out this curve to the charger, it can follow this curve, and that means it can always charge at the maximum rate that the battery can allow. And that gives you the fastest recharge time. If we're using a conventional charger that does not have the software built in to Recharge the battery, we typically set the charge rate down low, maybe 20 amps, and that would give us a slower recharge time. But we kind of look at the temperature requirements for the room and say, okay, how low does the current have to be to stay under this curve? And so we just set the maximum current. That typically we recharge with a conventional charger in 6 to 10 hours instead of recharging in maybe a little over an hour. We talked about the need to know your temperature, both for that previous slide to know how fast we can charge, but also for capacity. If you look at any battery data sheet, it's going to tell you that the battery can work from some number, say minus 30 degrees C to plus 40 degrees C. But what's often overlooked on a data sheet is that if you're going to run that battery at 0 degrees C, and you have to know that so that when you size the battery, because if you discharge the battery at 0 degrees C, you're only going to get about half of the capacity. So you have to size knowing the temperature of the environment. This is just a look at the modularity of the system. We can stack up the number of modules you need to get to the voltage requirements. So we can do 120 volts, 240 volts, 380 volts, 480 volts, anywhere up to a float voltage of 600 by changing the type of the modules and the number of modules. And then we can add strings to get to the amount of power you need or the amount of runtime or energy that you need. So it's a very flexible system. These are a whole list of applicable standards that the Flexion system was designed to. In the US, the most important one is the second one from the bottom. UL 1973 is the UL listing for a stationary battery, a stationary lithium-ion battery. And we're fully compliant with UL 1973. There's a lot of other things. UN 3480 is the transportation rules, so that we have to certify that the battery can be shipped by air, sea, and plane or road. And it has to go through a transportation test. So depending on what codes and standards you need to meet, we probably can support that. I have this slide in here for a break. Does anybody need a break? Is anybody out there? Just at least one person tell me I'm still here and I'm listening.
Andrew raised his hand, so he can hear you.
All right. All right. It's been dead silent. I got worried. All right. Any questions so far on what I'm going to go into next is building codes. So we can look a little bit into the building codes, but do you have any questions about the battery or contactors, diodes, sizing, any concerns?
I don't see anybody raising their hands currently. A bunch of people did raise their hand. Andrew did, and Dave did, and Don raised their hand. So I think everyone can hear us and knows how to work the hand button, and I don't see any questions currently. So
okay.
I think you're ready to go, Dan.
All right, we'll just we'll take a quick look at some building codes. Building codes have been adapting very quickly in the last 3 to 5 years. But in some areas, they lag 3 to 5 years behind when they release to the new code. So you might be in one area and they're using NFPA 1 or 2018 code. You might be in another area that's using the latest code. So you have to know where you're going to do this installation and who you have to please. And if you're a utility customer, I think you typically are your own certifying agency. So you're not really meeting with your building code people as much as your own internal experts and engineers. So it kind of depends on the market and the type of customer and the area of what codes you're going to have to apply. Prior to 2018, the IFC had some reference to lithium-ion batteries here in this column, the second from the last column. But you can see there's the only requirements they had was signage, seismic protection, and smoke detection. There's very little prior to 2018. So in some areas, they're still running on 2018 code. After 2018, two things. The IFC, well, 2018, we're still running with NFPA 1, Chapter 22, IFC 608, and the 2018 editions. But in the 2018 edition of the IFC and the new one called NFPA 855 came out in 2019, very similar to the IFC. And they added a lot of rules about how to install lithium-ion batteries in indoor applications, outdoor applications. A lot of this was driven, the NFPA was driven to get something out after a number of fires happened in energy storage containers. Pretty famous example there in Hazard, Arizona. This is a summary. It applies to systems over 20 kilowatt hours. This is both the 2018 IFC and NFPA 855. They pretty much tried to duplicate each other. Over 20 kilowatt hours, these rules apply. They define an array size at 50 kilowatt hours. In between those arrays, they want a 3-foot space between the arrays. So for every 50 kilowatt hours of batteries, you have to have a 3-foot space. And this was to try to prevent propagation from cabinet to cabinet to cabinet. They have a maximum allowable quantity per fire area of 600 kilowatt hours. So 600 kilowatt hours, and then firewalls, like a 2-hour firewall, and then another room for more 600 kilowatt hours. This is a very big battery. For us at the data center level, this is about a 2 megawatt battery. This would be probably 18 or 20 cabinets. This is a big battery. They put some limits on which floor of the building you can put it in because they want the fire trucks to be able to access it. So there's a limit of 75 feet above grade and 30 feet below grade. And then they have this proviso that says the AHJ, or the authority having jurisdiction, can approve closer spacing if they have a large scale fire test report. So now we're going to talk about the, well, we're going to get to that large scale fire test. Some other things, they require that the lithium-ion battery has a battery management system that monitors all the cells and has the ability to transmit the alarms to approved location. They require that you do some risk and failure mode analysis for the room, and that considers your other things like fire suppression, gas detection. They want a risk analysis done of that whole room, like a DFMEA or a risk analysis. For gas detection, they want to alarm for 25% of the LFL, and they want that gas detection to activate ventilation so that you never get above the LFL levels, so that you are exiting this was the main problem with that explosion that happened in Hazard, Arizona with the energy storage container. The flammable gases that were vented from the batteries built up inside the container, and then when they opened the door, the gas air mixture got just right and exploded. I don't know if I have, there's a big report. I might not have all the details. You can read that report, but that is why the gas detection is supposed to activate the ventilation system to exhaust the gases. I should say lithium-ion batteries do not gas in normal operation. They only let gas out of the cell in a venting or thermal runaway situation. So if the cell gets very hot and the pressure builds up inside it, it will vent the electrolyte out into the air. That's the venting that we're talking about. Normal operation, there's no venting at all because it's completely sealed battery. So what is large scale fire testing? There's a UL test method called 9540A. It's a large scale fire testing. And the goal of this is to determine what the risk of fire propagation, cell to cell and module to module, the amount of heat and gases that are generated, and what your fire service strategy and tactics should be for your design of your room. Depending on the outcome, it will determine whether or not you need that 3-foot spacing between your 50 kilowatt hour arrays. So it starts out with a cell level test. The cell level tests are done to make sure that the test lab knows how to put the cell into thermal runaway. In the case of Flexion, we had to put heaters on multiple cells. We put heaters on 3 cells that surrounded one of the cells in the center of the module. We had to heat those 3 cells up until the one in the center vented and went into thermal runaway. So you have to put the cell in thermal runaway to be able to do this test. And the cell level test show UL in the laboratory how to do that. Once they know how to do it, they proceed to the module level test. And what they're looking for here is to see if you get cell to cell propagation. And with our iron phosphite, we did not get any cell to cell propagation beyond what we forced with the heaters. So that one cell that we got to go into thermal runaway did not heat up enough to cause another one next to it to go into thermal runaway. It says if you pass, if there's no cell to cell propagation doesn't occur and there's no need to perform unit level testing, that's not true. You have to also meet one more criteria that says there is no thermal or no flammable gas emitted to be able to stop at the module test. But all lithium-ion cells, the gas in the electrolyte is flammable. So I don't know of any lithium-ion battery that can stop at the module test. This 9540A can be done for other chemistries, sodium nickel or some other chemistries that might not have flammable gas, but lithium-ion batteries are always going to move on to the unit level testing at least. This is a cabinet level or unit level test, and you have to have 3 cabinets together. One is the target, or one is the cabinet where you're going to initiate thermal runaway, and then 2 beside it are targets to see if the temperature or any propagation go from cabinet to cabinet. This test passes a difficult word. If you don't have these things, you don't have to move on to the installation level test. But the test is actually not a pass-fail test. It is a test method and a report that's generated that tells you all of the temperatures and whether or not you got propagation, whether or not you got explosion, whether or not you got flame outside the cabinet. what the maximum temperatures were on the outside of your cabinet and on the surfaces of the walls around the cabinet. It's a test report. It's up to the AHJ to take that report and decide whether or not he will allow you to go to a closer spacing. UL will make a recommendation that says, we don't believe spacing is necessary with this battery, if that's what they believe. But it's up to the AHJ. NFPA left the code enforcement people in control of whether or not you can go to a closer spacing. This is just a list of codes and standards that you might run into. NFPA 855 is the newest and biggest, the one that most everybody is going to. And like I said, if you're a utility customer, you can tell me, but I don't believe you're necessarily required to follow this. I think it's up to you to have your own PEs and your own authorities inside your company design your systems. At least that's what I've been told by the utility that I work with in the Southeast. And that's all I have. Thank you for your time, and I'm available for questions if you have any.
If anybody has any questions, they can either raise their hand and I can unmute your line, or you can type in a question and we can answer that question as I read it. And it doesn't look like we have any takers as of yet, but we'll give it another 30 seconds. And then if not, we will end the webinar. And again, thank you on behalf of HM Cragg for attending and learning more about the Saft lithium-ion batteries and the capabilities that they have for utility customers.
Yeah, and if you have any requirements, you can send them to HM Cragg and we can size the battery and provide you quotes. And I should probably mention also I've mentioned smart chargers. We've got smart chargers available through LaMarche and Primax, smart UPSs with Amatec, and those are all just the industrial guys, Benning. So we've got full integration and testing and experience with those companies, and then a number of the commercial UPSs, Meppy, Eaton, Schneider, have tested at the data center type level for higher voltage systems. So we can help advise you who we've been working with to provide the smart chargers. And but if anybody has any questions, they can get a hold of Dean or and contact me. And I'm glad to do this type of presentation again if you have other groups. And I thank you for your time. And I'm here for your support. If you have questions in the future, you just want to have a conversation with me, just reach out.
Yep, I do not see any other questions, Dan. So I think we will wrap it up. And again, yep, thank you for attending. If any questions come up after this, feel free to reach out to your HM Cragg rep, and we will get it over to Dan, and we can have another conversation if needed. Thank you for all attending.
All right, thank you. Bye.